Okay, welcome back, everybody. Sorry for the delay. Had a little bit of a technical problem, but we got it corrected. All right, we ended up. Any questions before I continue? Chapter 122. No, okay. Well, we ended up on page 22, based on my notes of chapter 1. So let us continue with that. The plan is, let's finish this up, this chapter. Then we'll jump into the next chapter and do probably knock that one out too. Then focus next Wednesday on chapter 3, and then prepare you for the first exam, which would be that day. Now, I probably what's going to happen, given the time scale, I may have to move the exam to the following Friday, given that I want to make sure I give you more time for that last chapter. But we'll see how it goes, okay? All right. We ended up here on, give me 1 second here. Zoom did an upgrade and kind of change things around a little bit. Okay. I'm assuming you can see the screen. Anybody cannot see it because, like I said, they did an upgrade, and the layout's a little bit different than it was last Wednesday. All right. Well, okay. We're talking about chemical change. So this first chapter is kind of introduce you to okay. Thank you, Kimberly. Some of the concepts of the of chemistry, kind of tell you a little bit about it, and then the next chapter we jump into the math part of it, and next 2 chapters actually, and then chapter 4 we get back into the chemistry. All right. Well, we do need to get into a little bit of math, not a lot, but we'll see what that's all about when we get there. So, indicators of a chemical change. Okay, how do we know if something underwent a chemical change? And there are a lot of instrumentations in any chemical reaction that you can do to tell you that, but these indicators are something that you observe in the lab. Okay, for example, obviously burning. Anything that burns or rusts is a good indication of a chemical change. Recall that a chemical change is any process by which a compound undergoes to actually destroy that compound completely and to make new products. It's not reversible. It's a one-way street, okay? As compared to a physical change where the chemical component, the chemical compound is still the same before the process and after the process. You have not done anything different or any change to the chemical composition, how that's put together. Okay. Something like a release of gas bubbles, where normally there's no heating involved, there's no heat given off. A good example of this would be an Alka-Seltzer tank. You take Alka-Seltzer, which normally consists of baking soda, sodium bicarb, and maybe a little bit of acid like citric acid, and they're in the solid form. And so when you take the tablet and you dissolve it in water, these chemicals get released in solution. Now there is a chemical reaction that proceeds. The acid reacts with the base. One of the products of that reaction is gas, which is carbon dioxide, and that's what you see in the effervescence, in the bubbling action. Formation of a solid. There'll be reactions where you have the 2 reactants that are clear and not cloudy. They may be colored or not colored, but they're cleared. And then the moment you put them together, they get cloudy. That cloudiness is what is called a precipitation. a new product was made that shows, little solubility in the solution, which 9 times out of 10 it's aqueous solution, and therefore falls out of solution. Okay. In fact, there is one type of reactions of the 6 types that we're going to eventually talk about. The first one, the bubbling example with the Alka-Seltzer, and that is a neutralization reaction. That is one type. Another second type of the 6 is this one, which is called a precipitation reaction. Okay, but a lot more on that down the road. Or you can get a reaction that emits heat. You can go to the, the pharmacy and purchase a hot pack or purchase a cold pack, and you get that pack, and what you do is you smack it, and depending which one you get, one of them will release heat and get warm, so you can put it on sore muscles and whatever you need to use it for, or it could get cold. Okay. Another example of not another, but an example of something that emits light would be glow sticks. Glow sticks are a classic example. If you look at the glow stick, you have a piece of plastic tubing with a liquid, but inside that there is a glass tube sealed that you need to break. You bend that the glow you bend it and break the inner tube, the inner glass tube. Chemicals release, and one of the products of that particular process is light. Okay, firebugs, another example. Firebugs, they have a chemical reaction occurring in their hiney that is causing this emission of light. All right, change in color. Again, you may have 2 clear solutions beforehand. You mix them together, and maybe now it's orange or purple or green. Okay, that's a good indicator that there has been a chemical process. Or an odor. Okay, be it a nasty smelling odor, which a lot of compounds are, or a very good smelling odor. Like a good example of that would be what we call esters, like wintergreen, banana oil. These chemicals, they're made from 2 types of chemicals, which is called an organic acid and an alcohol. There are different types of alcohols. By themselves, those 2 components, some smell not too good, some smell neutral, but the moment you put them together, they have the very nice smell, wintergreen, which you smell spearmint and banana oil, and numerous others. Okay, let's see. All right, so those are some indicators that put 2 reactants together and something happened. Okay. Now, a good example of a chemical reaction is between sodium metal and chlorine gas. When they react, they produce a salt that we're all familiar with, something that you put on French fries, good old-fashioned sodium chloride. Now, keep in mind, when we use the term salt, okay, in general, people tend to just think of sodium chloride, but that's not true with respect to chemistry. We're going to find that the term salt is utilized in a large number of different types of chemicals other than just sodium chloride. Okay, very, very specific types, and that type is of all the chemistry involved out there. There's only 2 types of chemical compounds. One of them is that something is sodium chloride. Okay, well, here's the thing. Where'd it go? There we go. All right, so here's an example. We have sodium metal, which is a very reactive metal. Here is a picture of it. It's soft, nice and shiny like a typical metal, but it's so reactive that to utilize it, we actually store it in mineral oil. We can't just leave it open to the air. because it will react with the moisture. In fact, if I take some sodium and just add a little water to it, the reaction that proceeds is very vigorous. And what happens is you give up a lot of heat and you create hydrogen gas. The amount of heat that you generate is enough to ignite the hydrogen gas, and you might get a little pop, a little explosion. Okay, so, and that is the sodium. Okay, chlorine. Here's an example of the diatomic elements. Diatomic. Those are those elements, and there's only 7 of them. We're going to go over them. That because of the nature of the beast, these 7 cannot exist by themselves. We have 118 elements. Of these 118 elements, 7 must combine with another one of itself to be stable. Okay, and so we do that by writing a subscript 2. So you see it Cl subscript 2, which tells you that there are 2 chlorides bonded together, and normally we will put Cl, a line to represent that bond between them, and then Cl again. So, but in lieu of writing that all the time, we put a subscript 2. Okay. Well, chlorine normally is a gas. Okay, this is actually a solution of chlorine, but it's a gas, a yellow colored gas. More importantly, it's a poison. Okay, it's a poison. A lot of municipalities have water treatment plants in their area, and and what they do is they may not. Everyone's different. They may use chlorine. Even swimming pools, some large swimming pools use chlorine to disinfect the water because it's very effective in treating the water to get rid of bacteria and such, viruses. So, but the possible downfall is if they have a chlorine leak, you can smell it. It'll smell like, it'll smell like chlorine. Like if you go in the pool that's been chlorinated, and it's a gas, and it's a real dense, can be a real dense yellow cloud. You see that, get uphill quickly because it gets in your lungs and it will literally destroy your lungs. So what we have here is an example of a metal, sodium metal, okay, very reactive, especially with water. And we have a non-metal, we're going to learn the difference between this metal and a non-metal, a very poisonous gas. And then when they react, guess what? We form this compound, which is you can put on your French fries, sodium chloride. Okay, and the surprising thing, not surprising, but the awesome thing from my perspective is that occurs is that there are just 2 electrons. I remember the model of our atoms are we have the nucleus, which consists of proton and neutrons, and then orbiting around the electron are the electrons, okay, which are so tiny. Basically, they have a mass of 0. Okay, so we have these electrons orbiting around, very small. Here we have 2 tiny electrons that get transferred from the sodium to the chlorine to create the compound sodium chloride. And totally different compound, totally different properties. You can see they even look different, okay? All right, and it's analogous to, like the Jekyll and Hyde scenario, where if I were to lose a strain of one strain of my hair, I turn into a completely different being. And that's how much power, that's how much influence these electrons, though they're so tiny, have on chemistry. Okay, so this is a very good example of one. All right, so now with that being said, you could be given these reactions written as follows, and then be asked to, is it a physical or a chemical change? Okay. Now, granted, you may not know at this point in time what these chemicals are, and that's okay. All right. Hold on 1 second, please. That's okay. But, we have the power of observation, okay? We can see here that, if you recall, we have an arrow, a chemical arrow here. Okay? It's a one-way arrow, okay, at this point, but it could be a two-way arrow. But the point is this, you got the arrow, which means on the left side is the reactants, and on the right side are the products. Yes. So the first one you're saying your physical, that's good, that is correct. But let's expand on that. We can see here that if we look at the reactants, NH3, we may not know what that chemical is. That's okay, I'm going to tell you what it is, but right now you can see it's NH3. You can see that its physical state is a gas. And then in the product side, we still had the same chemical structure, the makeup, NH3. But it's physical change. There has been a physical change because it went from gas to the liquid. Okay. Now, NH3, I'll let you know what that is. It's called ammonia. Okay. So here, ammonia went from the gas phase to a liquid phase. So going from gas to liquid, the chemical structure has not changed. Oh, we got questions here. Yep. And so being that it is it's a physical change because the chemical makeup did not change. Okay, so we have a physical change, and I thought I had them all separated, but I guess not. Okay, so first one, number one, is a physical change. Okay, if we look at number two, which again is ammonia again, the difference this time is on the product side, we have a plus symbol, which tells us there are more than one product. That in itself, just the fact you got a plus there, you break it down, that means that ammonia, NH3, was broken down to its elements of nitrogen and hydrogen. Now we put numbers, coefficients on them because remember, the conservation of matter, okay? And those coefficients tell us that there are two molecules of ammonia to begin with. And then after the process, there's one molecule of nitrogen and three molecules of hydrogen. Altogether, we have 6 hydrogens in ammonia, okay? So you can see NH3, NH2 plus 3H2. My dog here trying to get into the trash. There are 2 molecules of ammonia, which written as so. So you can see there are 2 nitrogens total. On the right side, we have 2 nitrogens, okay? And we have a total of 6 hydrogens as a product side. Excuse me 1 second. With trash hole. All right, so we got a total of 6 hydrogens on the right side. Okay, we have a total of 6 hydrogens on the left side. We have 2 nitrogens on the left side and 2 nitrogens on the right side. We're going to learn about these 3 lines at a later date, but that's how we write nitrogen. So what we say that this is a balanced chemical reaction. Okay. We're going to learn about balancing chemical reactions because the conservation of matter governs that. If I start off with 10,000 atoms as a reactant, I'm going to end up with 10,000 atoms in the product side. They may be in different forms, but they're going to still be whatever atoms they are. Okay. Okay. So now looking at number 3, at first sight, we might think, looks like water, right? But the difference is this: there's two oxygens and 2 hydrogens, which is not water. You're probably familiar with this chemical here. You probably, may not know what that is, but you probably have used it. Okay, if you ever cut your finger, you may have put some on there. You ever tried to maybe lighten up the hair? This is an active ingredient in as a disinfectant, active ingredient in cleaning up wounds, active ingredient in blonding up your hair. That's called hydrogen peroxide. But at this point, that's not important that we know what that is. But that is hydrogen peroxide. We look on the right side. We see here that hydrogen peroxide was broken up. Okay, that implies it is a chemical change because the starting material was broken up into different components. Okay. And it went from H2O2 liquid and creating hydrogen gas and oxygen gas. So definitely a physical change. Excuse me, chemical change. Number 4 also is start off with hydrogen peroxide. Okay. Hannah has a question. H2 is the same thing as H. Okay, H2 means that it's one of the diatomic elements. So there are 2 hydrogens bonded together. Okay, so it's still hydrogen, but the way it's written is H2 because at our room temperature, 25 degrees here on Earth, it exists as a diatomic species. So yes, we write it as this, H2, which is basically, if I wrote it longhand, if you will, I put a line between them because that line represents a bond between 2 hydrogen atoms. So instead of doing that all the time, we just simply put a subscript. And that will be true for, say, Cl2, which is chlorine. We're going to have Br2, which is bromine. And we'll get to the rest of them here in a bit. Oxygen is another example, and so forth. Yes. All right, so number 4, not to be mistaken, it's a good question since you brought that up. Not to be mistaken when you just have hydrogen bonded together. Now, if you look at the way this is written, you might think, H2, maybe I'm looking at this, and the answer is no, that's not correct, okay? What is happening here, if you have another atom immediately following the H2, then that means that these hydrogens are bonded to these other atoms, just like water, H2O. That is not hydrogen gas, H2, because right immediately afterwards, we have another atom, which tells you that those hydrogens are bonded to those atoms, okay? All right. And so number 4 is a physical change. Why do I know that? Is because when I look at the chemical makeup, it is H2O2 as a reactant, it is H2O2 as a product. Okay. Furthermore, I can see the physical state changes. It went from a liquid to a solid, so that is a physical change. Okay. Number 6. Again, you may not know what that is, but it simply is C6H6. Okay. Do you remember the general name? We had spoken earlier about compounds that contain only carbon and hydrogen. You recall what that is? What the general term I utilized to describe a compound that is made up of nothing but carbon and hydrogen. You use a lot of it to run your vehicle or your motorcycle. Remember the term hydrocarbon? Hydrocarbon. Okay, that's a general term to describe any chemical that is made up of nothing but carbon and hydrogen makeup. Okay, so this is a hydrocarbon, and C6 consists of 6 carbons and 6 hydrogens, and then before and after basically the same thing, okay, structurally or chemically. And so that implies that we have a physical change here, and we verify that by the physical state because you're going from a liquid to a gas, which, by the way, liquid to a gas, remember what we call that? Liquid to a gas. what do we call that? Vapor, yes, that's one of the terms. It could be vaporizing, it could be boiling, okay, or evaporating, okay. All right, so, and the main takeaway about this exercise of these 5 different compounds, reactions, as you're saying, is to recognize the reactant, the way it's written, recognize the products, the way they're written, and if they're the same before and after, then we get a physical change, okay? If they're not, then is a chemical change like number 2, where ammonia was literally broken down to create 2 more different products. And that's what happens with chemical changes. Normally they're broken down to a minimum of, at least two different material compounds. Okay. Now, I think this slide here is pretty self-explanatory. What it is, we use a lot of diagrams to describe, what we're looking at. Obviously, these diagrams in chemistry are just models of what we think they may look like. And normally you'll find them that they're written up as, as spheres, as a compound, be it an element or even other compounds are written up as circular circles, okay? But that just represents an atom, okay? That's all it's doing there. All right, so if we look at matter, which started from here, and we come over here to the right side, we're dealing with mixture. So the way we represent a mixture, we can see here on the left side that we have these dark balls here, which would represent an element, okay, of some sort. Whoop. Right pin. Okay, so the dark ones will represent an element. Okay, then we have these 2 that are combined together of the same color. What that represents, again, an element, but more specifically, a diatomic element, okay? Though there's 2 together, remember when those 2 atoms are put together and they are the same color, well, here we got color, but it could be gray, shades of gray. But if they're the same, that would suggest that we're looking at the same atom, therefore it is a diatomic element. Okay, so we got a mixture here of an element and a diatomic element. On the right side, you can see you got 3 different colors. There's kind of green and red, and then I guess the dark brown from my screen, dark brown to black color, all by themselves, nothing bonded to them. So it looks like they're all elements. So we got a mixture of 3 different elements. Okay. Come over to the pure substances. So if we look at compounds, remember that by definition, a compound is a moiety that consists and made up of 2 or more different elements. So if we look at these here, where we have a red circle in the center and then 2 yellow, looks like Mickey Mouse ears here, right? Looks like 2 yellow circles on the red. That would be a good representation of H2O, where the red represents the oxygen and the yellow ones represent the 2 hydrogens that are bonded to the oxygen, okay? Now with compounds, we're always going to have one element that is the central element, and everything is bonded to the central atom. So in this case, oxygen is the central atom, and then the 2 hydrogens are bonded to the central atom. Looking at sodium chloride, you might say, okay, looks like we have a diatomic, but they're different colors, okay? So yes, it's diatomic, but it's a diatomic compound because it's made up of 2 different colors. And this is a good representation of, let's say, sodium chloride, good old table salt, okay? When we're dealing with the elements, recall that we either be a singular element that stands by itself here at room temperature. It's stable all by itself. It doesn't not require to be bonded to another one of itself, like the diatomics right here. which is oxygen, for example. Okay. All right. So you will see a lot of diagrams to represent the elements and compounds and mixtures and so forth. A lot of diagrams. So let's talk about the element. Let's talk about compound and the mixture. The element is just simply one type of atom in itself. Okay, it could be either single elements like I discussed, or it could be the diatomic like oxygen. We can't break these down any further chemically. We can break them down to the subatomic particles. Atoms are made up of, at least the subatomic particles that we're going to talk about, is proton, neutron, and electron. Now we can remove electrons, we can add electrons, we can even play with the protons and neutrons, but when we do that, we create different species, okay? So if we take an element, we try to break it down, we start playing with the subatomic particles. Unlike the compounds, which compounds are made up of two or more different elements. We can take a compound, break it down to the elements. Classic example would be we can take water, which is a compound, okay, made up of two more different elements, and literally break it down, undergo electrolysis, and break it down back to oxygen and hydrogen, okay? That's a indication of a compound. We can break it down to elements. All right. And then, of course, pures, materials, all the particles are the same. There's nothing to separate from anything. It is a pure component of whatever you're looking at. Okay. Unlike a mixture, which is made up of two or more particles of pure compounds all mixed together. And we can actually go in there physically or chemically remove the different components of a mixture. Okay, so some classic examples of mixtures are, for example, all metal alloys. Metal alloys, the term alloys, just by the term itself tells you that these are metals that are a mixture. For example, 18 karat gold. It's 18 karat gold tells you that it is not 100% pure gold all by itself. And the reason that's the case, definitions, let me back it up. Okay, how's that? The definitions, oh, by the way, I have yeah, no worries. I do have FYI, if not, I'll go check, but all my these PDF files that I'm utilizing, I did upload them to the course website. And some students like to take them and print them out and use them as notes, totally up to you. So you do have all these notes readily available, my PowerPoint slides, as PDF files. Okay. Yeah. Right. You got it. Okay. So as I was saying, 18 karat gold is not 100% gold all by itself. And simply because gold in itself is very soft and doesn't lend itself well to making jewelry. And because it's so soft, you make a ring, first time you smash your hand, you're going to smash that ring on you. So what happens is other metals are put in it, other materials put in it to give it strength. And we have what are called alloys. Brass, for example, is not a metal in itself. It is a mixture of both copper and zinc, mostly copper, but has some zinc in there, and some other trace metals. And steel is not pure iron in itself. Pure iron, 100% iron, is very soft material. Does not lend itself at all to make building materials because it's so weak. And so other things like carbon are placed into it, some other metals. And what that does is it allows it to gain strength. So we're making alloys, sand, granite, tap water. The tap water that's come out of your sink definitely is not pure. It is a mixture of all kinds of things, all kinds of salts. Notice I use the term salt, like calcium carbonate, sodium chloride, potassium. Not to mention, you may even have some organics in there, that pesticides, herbicides, etc. And the air around us is an example of a mixture. And we got all kinds of nitrogen, oxygen, carbon dioxide, good examples of mixtures. Okay. An example of pure material is you get some salt, undergo some cleanup process, you can get nice pure 100%, or at least close to 100%. Very rarely do you get something that's 100%. You come close to it, 99.999, but 100% is a pretty tough call. A diamond. Well, granted, a lot of diamonds that we have in jewelry are not 100% pure. But there are some, but not a lot. The thing is about diamonds, that the takeaway here, that is that pure carbon is carbon in itself is what is the major component, the main component of carbon, okay, of a diamond, I should say. It's the same carbon element number 6, that you have on your skin, that you maybe use in graphite. Graphite is a dry lubricant used for multiple things, but in all three cases, it's carbon. But carbon in the form of diamond is the toughest thing on earth. And one may ask, well, why is that? Well, I'm glad you asked, because the way the atoms are put together relative to each other has a large effect as to the properties of the final product. The diamonds the carbon atoms are put together such that it gives them the maximum strength, okay, giving you a material that's the hardest thing on earth. We can do that with a lot of chemicals. We're all familiar with polystyrene, used a lot for cups, very soft material. But if I play with the chemistry of polystyrene, which by the way is made up of nothing but carbon and hydrogen, it's a hydrocarbon. By playing the way I make polystyrene, I can make it such that the density is much higher and strong. I can use it to build bridges with the material. So, and it's made up of nothing but carbon and hydrogen. Okay. Distilled water, yes, that's clean. Again, may not be 100%, but pretty close to it. And distilled water is simply water that you actually boil it. It boils, it goes up to a condenser, and then recondenses, and you collect it on the other side. And that becomes a lot purer. A lot of times to get it even more pure, you redo it again, do another distillation, or you utilize these big or long columns that will allow us to do a series of vaporization and condensation each time along the column. The point is, by the time it gets to the top of the column, it is pretty clean. Okay, very clean. And an element, a pure element like mercury, some examples. We write diagrams. Again, this time these are in grayscale to describe an element. You can see in the far left, that's a description of an element, specifically a diatomic element, because we got 2 of the circles, which are the same color, which are the same size, which would then allow you to determine that that is a element, specifically diatomic. Then the one in the center, you can see here that the light one, there it is. This here is the central atom, the white one. Okay, and then we have these dark ones bonded to the central atom. And so again, that indicates a compound. And on the right side, we have a mixture it looks like two different elements depicted by the gray ones, and then we have a dark one here, so that represents two elements. And then we got the good old Mickey Mouse ears of a compound. So we got a mixture here of two elements and a compound. All right, so given diagrams, you may be asked a question. What is A? Well, for example, A indicates an element, specifically a diatomic element, okay? B, we have a dark circle with three lighter circles around it, okay? Again, that means a compound because it consists of two different elements. And so that is a good example of an element. In fact, if we wanted to be a specific example, that could be ammonia. Ammonia, we're going to learn the structure and how to put this together. You know, that dark one could represent nitrogen, and then those three clear ones represent hydrogen, okay? We're going to learn how to put this, well, I just wrote it like this. We're going to learn how to put these compounds into some type of a structure, okay? So, and learn about the geometry. All right, so we got a compound. C looks like a mixture, specifically of elements, okay? And then D, again, it looks like it's all dark circles, so that would represent just a pure element. Nothing else in there. E is a good example of a compound because we have a dark and a clear circle, white circle bonded together, okay, which represents a compound. Again, not a mixture. And F, because we have at least two different compounds and an element, specifically a diatomic element, and that's what is represented in F, okay? And then finally, again, not finally, but G is a good representation of another mixture, which consists of an element and a compound. And then H, since they're all the same, all circular, nothing else involved, we got an element. In fact, we can even further classify it by the way it's written. It's very structured, very ordered. We could even say that that's a solid because the way they're all put together and very structured. Unlike the others, you know, they could be liquid, they could be gas. Can't make much of a conclusion there. Okay. All right, so here's some more pictures of an element, the models of an element, and either being monatomic, meaning one element, or diatomic, meaning two elements bonded together, and a compound. Okay, which brings us to elements. We're going to talk a lot about elements, okay? So let's briefly introduce them. Each element has their own unique name. There's 118 elements, okay? And each element has their own unique symbol and their own specific number. Let's, we have a new share. Let's bring up the periodic table, okay? All right, so you can see here, let me zoom in a little closer. CR, which is chromium, the periodic table that we give you, which by the way, if we're gonna eventually do calculations with the elements, so please use the numbers from our periodic table. What happens is, yes, there's numerous other periodic tables out there giving you different numbers, slightly different numbers. And then if you use those numbers and then put your answer into Canvas not being the smartest software around, your number may be off just slightly. It may treat it as incorrect. Okay, so using these numbers You shouldn't have that problem. Which brings me to a point. If you ever put in a number, an answer that you know is correct, I have no qualms to go in there checking it. If it is correct, even though Canvas says no, giving you your credit. Okay. I do that because I know Canvas, if you add a space to your answer, Canvas treats it as incorrect. It doesn't recognize spaces. Okay. And if you were to write, let's say H2O to represent water, instead you wrote OH2, Canvas would say, no, it's incorrect. Well, that's not true. Okay. So keep that in mind. If you get no points and you know it's correct. So if we look at each symbol, there's 118, like I stated. Each one has a symbol, a letter. Some of them are a single letter. Some of them are two letters. Okay. Number one, each letter being two letter or a single letter, the first letter is always capitalized all the time. If it has a second letter for the symbol, then that second letter is lowercase. Okay. We'll have an example here in a bit to explain why that's important. The number, there's 118. Every element has their own unique number. The Ti titanium here is number 22. Okay, its unique number. Calcium is number 20. Okay, that bit of information is going to give you specific more information. In fact, it's going to tell you how many protons, how many electrons it has by that number. We'll learn that in a bit. The other number below the symbol is what we call the atomic weight. Notice that that number is a decimal number, okay? And every element there has their own unique atomic weight, which is the sum of the protons and the neutrons for that particular species. But there's more to it than that, but that's what I'm telling you at this point. The other aspect that you see on this periodic table, I labeled mine 1 through 7, okay? And you'll notice that if you look at the periodic table, you'll see that we start off with hydrogen on the far left, and then that's number 1, and then number 2 is in the far right with helium. And then number 3, we go back to the beginning of the periodic table with lithium. So that's how it goes. Starts in the far left, shoots to the far right. It goes until we reach number 18 here, which is argon. And then we go around the horn, so to speak, to number 19. But it continues all the way around. The numbers I have on my side here, 1 through 7, represent what we call energy levels. Think of them as just as they are, energy levels that have in them these electrons to these elements. The point there is the element hydrogen, for example, is in the first energy level as compared to potassium, which is in the fourth energy level, okay, number 4. That tells you that hydrogen is much smaller than potassium, okay? And potassium is much smaller than CS, which is cesium. And so going down the periodic table, you can look at where it's at relative to within the group and determine who is the bigger element simply by knowing what energy level that element is in, okay? So there's your first trend of the sizes of elements and using their periodic table. Not necessarily having to memorize all 118 and their properties, just knowing where they're at in the periodic table, and we can do compare and contrast as far as that property at this point. We're going to have a lot of other properties that we can learn and trends from the periodic table and where they are on the periodic table relative to the other elements. We can, in that radius is first example. Okay, so as I stated, first letter is capitalized. We got hydrogen, for example, is H, and capital C for carbon. The second letter is always, 100% always in lowercase, okay? All the time. if you were to inadvertently write it in uppercase, and then there's a difference here. C lowercase o is cobalt, okay, is an element. C capital O is carbon monoxide. Totally different species. Okay? Totally different species. And so if you write the O uppercase and you're thinking cobalt, then I'm sorry, the answer is incorrect. It's carbon monoxide. Carbon monoxide as that, and we know that carbon monoxide is a gas and very poisonous gas, totally different than cobalt. Okay, so getting the correct symbol is important for that element. All right. Now, most of the symbols do have English names. For example, H for hydrogen, as I mentioned, O for oxygen, He for helium. There are some that actually have their symbol comes from the Latin name. So PB is lead. Okay, it comes from the Latin word plumbum, which means waterworks, and AU is actually gold. Okay, AU coming from the Latin term aureum, meaning the golden dot. Okay, now be familiar with the first 20, and I'll go through the first 20 here in a minute. But on top of that, be familiar with AG, which is silver, AU, which is gold. Those two get mixed up quite a bit, AG and AU. Okay. Lead is PB, and then BR is what we call bromine. Notice the suffix INE, much different than the bromide, totally different. We're going to learn the difference time. Iodide, okay, as iodine as compared to iodide. Again, note the naming, and then mercury. Okay, let's go back, and we're going to go through the first 20. Well, obviously, number one, the very first element is hydrogen. Okay, we go to number two, opposite the right side of the periodic table is He for helium. Okay, then we go back to number three, energy level number two here. Li is lithium. Number four is Be for beryllium, and then we shoot across to B for boron, number five, and then the infamous C for carbon, very important element, and then next to it is N for nitrogen, and O for oxygen, F for fluorine, right below fluorine is Cl chlorine, right below is Br for bromine, and below that is iodine. Notice the ended INE, the ene. That signifies name-wise the element, okay, and not the IDE, which is found in a salt like chloride. So sodium chloride is the name for table salt, but it would be incorrect to say sodium chlorine. Chlorine means a totally different connotation. And then we have number 10 for neon, going back to the front first column, energy level number 3, and A for sodium. Sodium, coming from the term natrium. And then Mg, which is magnesium. We shoot across to number 13 here in the red circle for a good old Al, Al for aluminum. And then we have Si for silicon, P for phosphorus, okay, S for sulfur, Cl for chlorine, and then Ar for argon, okay? And then finally, we go back now to number 19, back to the first column. We're in energy level number 4, and we start with K for potassium. Potassium, Calum, I believe, was the Latin name for it, Calum, or potassium K, and then Ca for calcium, okay? Calcium. And those are the first 20. Now with time, obviously we're going to be using the other ones. For example, we're going to be using quite a bit Zn, which is zinc, Cu, which is copper, Ni, which is nickel, Co, here's cobalt I mentioned earlier, okay, and Fe is iron, cadmium, Cd, silver quite a bit. Here it is, silver. Here's gold below it. Here's mercury, okay. There's platinum, palladium, okay. So we'll be using those with time. So just want to introduce you to them. All right, so let's go back. Okay. I just went through the periodic table. It's just a different periodic table here. It helps you out with naming, but we'll get to that in a bit. Okay. Okay. Now, the physical states of these elements. Now, there's 118 elements. And you might think, oh, wait a minute, I got to learn the physical states of all 118. No, not at all. We're going to tell you, show you a periodic table and tell you by their position in the periodic table, you'll be able to determine which ones are the liquids, which ones are the gas, and which ones are solid, okay? All right, so at 25 degrees and at 1 atmosphere, which is, this is basically 1 atmosphere where we're at right now. If you go to Colorado, it's less than 1 atmosphere. The air gets light up there. Okay, so of the 118 elements, 2 of them are liquids at 25 degrees. Okay, so we start off with 118. Okay, 2 of them are liquids. We got 116 elements left. Okay, now of those, we have this group right here, 1, 2, 3, 4, 5, which is 5 of them, okay? Hydrogen and nitrogen, oxygen, fluorine, and chlorine, they are gases, okay? There's 5 of them. And then we have the special group called noble gases. All right, let's go back to the periodic table. The noble gases are the last ones. Okay, notice on the columns in the groups, we have Roman numerals. I just highlighted Roman numeral 3A, and then we go across 4A, 5A, and then all the way on the far right, okay, we have what are called 8A, okay? These are the noble gases, okay? And the reason they call them noble gases is because they're unreactive. They are inert. And the reason they are inert is because they all have obtained that magical 8 number. I got a lowercase c with a superscript hyphen, which represents the symbol for electrons. With the exception of helium, it has 2 electrons, okay? Okay, we're gonna learn that the driving force for chemical reactions is obtaining that magical Harry Potter 8, okay? That is what our models have shown, that when elements strive to obtain 8 electrons in their outermost shell, okay? As I stated earlier, our model is in the nucleus, proton, neutrons, and then the electrons are orbiting around the nucleus, and specifically now, they're orbiting around 7 energy levels, okay? Different energy levels. Well, all of the noble gases have, except helium, have 8 electrons around the outermost shell. That is the most stable configuration an element can have, okay? And under that configuration, it is tough to remove an electron because those 8 around it, all the electrons are being held on tightly. And it's hard to add an electron to something that has 8 around it because the only place it would fit would be in the next energy level. It would be one little electron all by itself in the next energy level, which is unstable. And Mother Nature, being Mother Nature, it does not want to be in an unstable state. It's going to get rid of it, okay? We're going to learn that all the other elements are wanting to obtain that 8 electron configuration around its outermost shell, okay? And depending on where that element is on the periodic table, it's either going to gain electrons to get that magical 8, or it's going to lose electrons to obtain that magical 8. And in the process of this gaining and losing electrons, they end up with a new charge. Right now, all the elements have a 0 net charge, okay? Because there's an equal number of the positive charges and negative charges. But the moment you gain electrons, you have an excess negative charge. The moment you lose electrons, you have now a net positive charge, okay? That is the driving force in chemistry. That is. So those noble gases have, and they're called noble because they're unreactive. There's 7 of those noble gases. If you look at the columns, there's 7 energy levels, or 7 noble gases, okay? Which brings us back to the number we had. And we say we had 118. We had 7 of them, and we have 5 of these. So there's a total of 12 elements. We had 2 that were liquids that left 116, and then 12 that are gases, okay? And liquids, which means that there's 104 elements that are solids, okay? So knowing which ones are liquids, knowing which ones are gases, and we'll tell you that the best, if you ever have to determine any element, is it a solid, liquid, or gas, you should be able to do that because with the help of, come on, this periodic table right here. Oh, let me clear up my mess here. Okay, the ones in yellow are the gases. So that is all the noble gases. And then on top of that, we got the fluorine, the chlorine, the oxygen, and the nitrogen. And then don't forget, way in the far right over here, hydrogen, okay? And then there's only 2 liquids, which is that one, which is mercury and bromine, okay? Remember, this is at 25 degrees, which is roughly room temperature. Obviously, if we're on the surface of the moon, in the physical properties, totally all gases, you know, all totally different, probably all actually plasma. Okay, so with that being shown here, you can now, if you're asked, okay, is this guy right here solid or liquid? Well, you don't have to go in there and memorize all the properties for every element, okay? Because you know where the gases are, you know where the liquids are, anything else is a solid, okay? Okay. All right, the diatomics. I mentioned earlier that there's only 7 of them, of the elements that are diatomic. At room temperature, 25 degrees, and at 1 atmosphere, they require another of itself to be stable and to exist here on Earth, okay? Someplace else, you know, they could be in a different form. All right, so we have this thing, have no fear of ice cold beer or have no fear of ice cold beverage, to help you out which ones they are. So the H of have represents hydrogen. The N of no represents nitrogen. F in fear represents fluorine. O of represents oxygen. I of ice is iodine. C is chlorine and not carbon. A lot of people think carbon. Carbon's not a gas. And then B of beer or beverage is bromine. These are all the diatomic elements. Okay, so that leaves 118. Everyone else is monatomic. So 118 minus 7 is 111 elements that are monatomic. Yeah, here on Earth, they exist perfectly fine all by themselves and don't have to be diatomic to exist. Okay, now, when we look at the elements, they're classified into 3 groups. That's it, 3 groups. We're going to have either a metal, okay, or a non-metal. And then we're going to have what are called semi-metals, or you may hear the term metalloids. Metalloids are those metals that have the properties of both a metal and a non-metal. Okay, now why do we need to know this? Because when we know the element and what it is with respect to it being a metal or a non-metal, it allows us to determine what type of compound they combine to form. And there's only 2 types of compounds. Okay, when we have a metal combined with a non-metal, I'm just going to label it NM, we have what's called an ionic compound. CPD is short for ionic compound. Good example is what we just talked about earlier, sodium chloride, good old-fashioned table salt. Sodium is a metal, chloride is a non-metal. Notice the term chloride, not chlorine, okay? When it's chloride, it is combined with something else. When it's chlorine, it is the element. When we have a combination of a non-metal combined with a non-metal, we have a compound that we call covalent compound. A lot more on this, so I'm giving you an introduction. That's why we have to, it's important to know who's metal, who's non-metal, etc. An example of a covalent compound would be, let's say, H2O. Okay, H2O, which if you look at it, hydrogen is a non-metal, oxygen is a non-metal. Okay, and so that creates what we call a covalent compound. Another name for it you'll see is called a molecular compound. Now, the big difference is as follows. With respect to sodium chloride, when they combine together to make a bond, they make an covalent bond, ionic bond, okay? Ionic compounds make ionic bonds. And think of those as 2 magnets, okay? Because the metal, and put this a long-term memory, metals lose electrons. Non-metals gain electrons. Okay, I remember, repeat that. Metals lose electrons, non-metals gain electrons. And by losing and gaining electrons, what is the result? The end result is they have a species that has that magical 8 that they are striving for. Furthermore, when you lose an electron, when you lose electrons, you end up with a positive charge. When you gain electrons, you end up with a negative charge net. Okay, it'll become clearer here in a bit. And when they put together, positive and negatives attract. They come together like 2 magnets, like these 2 magnets I got right here. And that is an ionic compound. Okay. When I take most ionic compounds and I put them in water, guess what they do? They break apart into their ions. This is what you're doing when you're drinking another name for the ions are electrolytes. If you take an electrolyte drink, you're drinking ions of these elements, okay, that either gain or lost electrons. Those ions are important in your body because they're the ones that have to carry current. Now, unlike non-metal combination, what they do is they think of it as this cap, okay? I'm a highlighter, here's the cap. Instead of being attracted to each other like ionic compounds, they actually form a bond. So here's one element, here's the other part. They come together and they form a physical bond, a bond that is shared, okay? Totally different properties than an ionic compound. They share electrons. So ionic compounds do not share electrons. They come together because of the attraction of the charges. And covalent compounds share electrons, okay? Either going to be equal sharing or unequal sharing. So we need to determine based on whether the element is a metal or non-metal as to what type of compound they can form, okay? And it's governed by, again, you can very quickly determine that by using the periodic table. Let me close this up. Again, it's positioned in the periodic table. If we look at the periodic table, you'll see there's a little stair step on the right side. That stair step represents where the metalloids exist, starting off here with boron, okay? You go down, boron, go across, silicon, and down, across, down, across, down, across. Now, 118, not sure if 118 is going to be, I believe it's a semi-metal. It's a fairly new element. They haven't had a lot of it to study its properties, but it's predicted to be a metalloid. So that's probably what's going to happen. So everybody in the little stair step right there represents the metalloids. These are elements that have properties of a metal and a non-metal, much like a mule. A mule is a result of a combination of a donkey and a horse. And therefore, it has properties of a donkey and properties of a horse, okay? Very important, semi-metals. We're not going to do a lot of work with semi-metals, okay? Most of our work is going to be dealt with the metals and the non-metals. That means here, once you identify the stair step, everybody to the left in blue are the metals, except hydrogen. Hydrogen is put in that first column for a specific reason. Okay, so remember that. It's not a metal. It's there for a specific reason. It is a non-metal. So what does that tell you here? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 non-metals. Oh, excuse me, 18. I forgot to count hydrogen. 17 non-metals, okay, and then we got 1, 2, 3, 4, 5, 6, 7, 8, 9 metalloids, and then what's left are the metals, okay? So knowing its position in the periodic table, we can determine what type of compound can be made from the elements. So if we combine carbon and nitrogen, guess what? We have a covalent bond, a covalent compound. If we combine calcium and oxygen, we have an ionic compound because it's a combination of a metal and a non-metal, okay? Which then lends itself to different types of properties that we're going to learn a lot more. See, a lot of this information is all, we're going to build on it, giving you this information, then we're going to take it to the point. Right now, we're focusing on the elements and the properties of the elements. And think of it as the letters of the alphabet. We're learning the letters of the alphabet. And then what do you do once you learn the letters of the alphabet? You start putting letters together to make words, right? And once we put words together, what do we start making after that? We start making sentences, and we start putting sentences together. Guess what? we make up paragraphs. And we're going to be doing the same thing analogously, I should say, that we start with the elements and we put the elements together to make compounds. And then we make other compounds that react with compounds to give us chemical reactions, okay? And then based on how the elements and which elements are put together, that tells us what type of properties these chemicals will have. And so everything's tapped in. And my hope is at the end that we put everything together. Not only that, we're going to be looking at the compounds that we put together and actually determine and calculate the geometry and what we think, what kind of structure they have based on where the elements are in the periodic table. So that's what I mean. That periodic table tells us a lot of information. Okay. We're almost done with this, and then we're going to take a little short break. All right, come on. All right, so some of the properties of metals and nonmetals, they tend to be, in general, very shiny materials in appearance, okay? Some metals are hard, some are soft. You can take them and really smash them, spread them out. A lot of the wires, for example, start off with a very thick cylinder, and they pass them through a die and really stretch it out, make it into the new diameter that they have. Okay, so all the metals are solids except mercury. Mercury used to be used a lot in what do you call these things for thermostats. Okay, they had a little switch. They had a metal that was heat sensitive, that was a coil that expanded and contracted, and then in the little glass was mercury. And so when this metal contracted, it rotated and it made contact with the mercury, and it turned your air conditioner off or on, depending on the temperature. Now everything is digital, totally different, which is good. Mercury is not good for the environment. Density, which is that ratio of mass over volume, is relatively high, okay? And the melting point, the temperature in which they soften up, is very high, very high. That's why a lot of metals, we need big old furnaces, like the steel mills, a lot of hot temperature to get them to melt, to make all these components. Metals are good conductors of heat because they're good conductors of electricity. They have a plethora, as they say, of electrons on the surface. They have a ton of electrons, and that allows electrons to be moved from point A to point B. In fact, FYI, the thought is that electrons travel through wire, and that's not the case. It's found that actually one electron kicks another electron out of a hole. It's sort of like that greyhound, what do you call it, gopher game, where these gophers pop up holes. Well, these electrons get popped out of one hole, move to another hole. So the point being, the electron that was created at the place that creates electricity is not the same electron that you utilize at your house to run something. It's all the electrons on the wire that have just been hopping from one point to another. Anyway, little side notes. All right, with respect to nonmetals, their general property is the ones that are solids that we can see are dull in appearance. If they're solids, they're brittle solids, and a lot of them are soft. A lot of them, as you saw, are gases, okay? And their density is overall low, especially compared to metals who have a high density. They tend to soften, melt at a much lower temperature than the metals, and they are very poor conductors of both electricity and heat. In fact, they're better insulators. For example, air, if you have at home a two-pane glass, in that center pane, between these two panes of glass is a layer of air, because air is a good insulator, okay? All right. Even our insulation is mostly, it's all, I know there's material in there, but there's a lot of air in there. And that's what helps insulate your home. Okay, so with that, be able to look at the periodic table and determine the name for the ones we talked about. Okay, as far as the elements are concerned, I'll be able to look at the symbol too, be familiar with the symbol. From slide 35, determine whether any element, not just the ones we talked about to be familiar with, but for any element, determine whether it's a solid, liquid, or gas. Okay, and based on this position on the periodic table. Determine again for any element whether it is a metal, non-metal, or a semi-metal, or the other term uses metalloid. And then whether the elements, which ones are diatomic and which ones are not. Okay, like I stated, there's only 7 elements that are diatomic. Okay. All right. Well, I tell you what, let's take a quick break. Okay. And let's see, I got 1:23. Let's come back about 20 till 2. And then we'll continue with the next chapter. Okay. And pause. Okay, let us continue. Chapter 2 deals with math skills. So we're going to touch on that. Fairly short chapter concerning with math and so forth. But before I do this, what I want to do is share with you a file, which I'm 99% sure I uploaded it, but it has to do with the metric system. Okay, and in science, we utilize the metric system. Now, this chapter and the next chapter, we're going to be using both the metric and the English system, and we're going to use it specifically to be able to convert or do conversions from one system to the other. And we're going to introduce a technique of doing that. And in doing that, I'll emphasize the point that that technique will be utilized when we do calculations for chemicals, okay, chemical calculations, all right? So let us begin with this. Now, we have 3 units that we utilize: mass, for volume, and for length, okay? For mass, our standard unit is G for grams, okay? For volume, it's capital L for liters, okay? And for length, we use M for meters. Now, the prefix like K or kilograms, the prefix K is always 1,000 times more than the base unit you're working with. So 1 kilogram. Okay, so 1 kg is telling that there are 1,000 smaller grams in 1 kilogram. The same is true 1 kl, 1 kiloliter. There are 1,000 liters in 1 kiloliter, and in 1 kilometer, there are 1,000 meters. Okay, 1,000 meters, and that is going above our base unit of grams, liters, and meters. Now, to go below smaller units than our base unit, we use the prefixes of D for deci. D for deci, which is right here. And one way to remember this is that there are 10 years in a decade, right? 10 years in a decade. So there are 10 decigrams in 1 gram. Okay. The next one down is centi, C-E-N-T-I, centi. One way to remember this is there are 100 years in a century, C for century. Therefore, there are 100 centigrams in 1 gram. The next one is milli, M-I-L-L-I, milligram, and one way to remember how many milligrams there are in 1 gram is milli stands for millennium. There are 1,000 years in a millennium. Okay, anybody know about the Millennium Falcon? Okay, side note. So there are 1,000 milligrams in 1 gram. So there's the prefixes, nice units of 10, 100, 1,000. Now, the one you may not know is, it looks like a letter U with a little dip there in front. That's called micro. There are 1 million micrograms, okay? 1 million micrograms in 1 gram. Now, if we take those same prefixes, the deci, the centi, the milli, and the micro, we can apply it not only for mass, move it over to volume and do the same thing. So we have 10 deciliters in 1 liter, 100 centiliters in 1 liter, 1,000 milliliters in 1 liter, and 1 million microliters in 1 liter. Okay, move it over, again, the prefixes over to length, which is meters, and we end up with 10 decimeters in 1 meter, 100 centimeters in 1 meter, and 1,000 milliliters in 1 meter, and 1 million micrometers. Okay, so what we have is here is conversion factors for you to go from 1 unit, go from grams to micrograms, and so forth. Now, every unit conversion factor, there is a ratio that we can set up. Okay, we can set up either in this form, where we have 1 kilogram over on the numerator and 1,000 grams in the denominator, or invert it and have 1,000 grams in the numerator and 1 kilogram in the denominator. This is using this particular relationship, but you can do that with every one of these, okay? Every one of these. Now, by setting it up in this manner, now you can set it up for a particular question, okay? By keeping track of your units, you would determine how to set up your conversion factor. For example, if you are given, let's say 50 grams, if you have 50 grams, the question may be, how many kilograms would that correspond to? Okay, if you have 50 grams of a material, how many kilograms would that respond to? Okay, so now you know the relationship between kilograms and grams is what I circled up here. And I can set it up in one of these two ratios. And I would recommend in the beginning that you set up both ratios until you become comfortable and you go directly to the ratio that you need. And so keep in mind, I have 50 grams, and I write that down first because that is what I'm looking for. And then I'm looking for units of kilograms, okay? Units of kilograms. That means I have a factor here that I'm going to set up. So this is what I'm given in the problem, okay? And this is what I'm looking for. I'm trying to find the answer, and I use the units that I'm looking for, okay? So that tells me that I set up my factor to multiply across. Now, obviously, I want to cancel grams, so I'm going to put grams in the denominator in that factor. And the units that I'm looking for will always be in the numerator. Why is that? Because look, as I multiply through, my grams cancel, leaving me with units of kilograms, which is what the problem asks for, okay? Now it's a matter of what numbers to plug in. So I'm going to use the factor on the left. So 1 is on top, 1 kilogram, and 1,000 is in the bottom. Now I know that I've had it set up properly. Now you might be tempted to take this 1,000 and make it into decimal form to put it in here. Don't do that. Just leave the numbers where they are and just either put them in the numerator or denominator, okay? Because sometimes what can happen, it gets all mixed up. So if you just leave the numbers where they're at, and you put either 1,000 in the denominator or 1,000 in the numerator, you're good to go. I check my units. Everything is set up properly with the simple algebra that we're doing with the units. Get grams cancel, leaving me with kilograms. Now the math is on you. It's a matter of you have taken 50 and dividing by 1,000 to give me the particular answer. Okay. So the takeaway about here is this: when you're given the problem as given here, you're always given the unit, a value, and a unit, and you're always asked what is the number in whatever new unit. And the thing to remember is your conversion factor should always have the unit you're looking for with that unit and the numerator right here. Okay. Because if I were to inadvertently use the other factor, okay, and let's say I multiplied by the factor on the right, let me change that color a little bit so we can see what I'm talking about. So if I were to multiply that 50 grams by this factor, okay, well, look at my units that I have. Look at just units, forget just the numbers, but just look at the units. The final units are grams times grams is grams squared divided by kilograms. But that doesn't even make any sense at all. And so that in itself should tell you that, no, I cannot set that problem up in that manner. I obviously needed to set up with using the factor on the left, okay? And so all these conversion factors allow me to go for one set of units. Now, obviously, if you're familiar with this, I can make factors that I can combine factors to make one instead of two or three. And if you're comfortable with that, by all means, go for that and use it. But do use the units to look at the problem to figure it out, because you may be asked a question as follows: how many micrograms are in 0.125 kilograms? Okay, and so this is what I'm given. I wrote that down. The problem's worked out here, but I'm looking for units of micrograms, so that is my final answer. Okay, unit-wise, so I set that up. Now, my first factor is I need to get rid of kilograms. Okay, so I set it up with the factor from the table above that I know there's 1,000 grams in 1 kilogram, and I set up with grams on top, knowing that my kilograms are canceled and I'm done with that part. And it leaves me with units of grams, which tells me I need a second factor here to get rid of grams. And I know based on the table up here that there are 1 million micrograms in 1 gram. So you can see how my grams cancel as I carry the math through. Okay, and so with respect to units, it is set up properly. And now it's up to you to type in the numbers and get the answer. Now, when we ask to show the work, this is the kind of stuff we're talking about. Okay, so this may be, for example, if a question like this might be worth 5 points. Okay. And so the breakup will be this, like be 1 point for the answer and units, okay? And the other remainder, 4 points, should be distributed amongst how you set the problem up. And so if you set the problem up correctly, and for whatever reason you typed in the wrong number in the calculator and you wrote a wrong number, obviously you're gonna not get the 1 point for the answer. But if you did set it up properly, you will get the 4 points, for setting up, showing the work. On the other hand, if you only just show me the answer and no work, well, the only thing I can give you is 1 point because you showed me the right answer. I'll give you credit for that, but I don't know, you didn't show me the work. Okay. And then the other factor is this: if you show me the wrong answer and no work, well, I can't give you anything because, your answer is wrong and you didn't show the work. So it's basically 0. All right. So you will get credit by showing your work and demonstrating that you know how to set the problem up properly. All right. And then the last part here is these are factors that you are given on the periodic table. Here's a question. All of the exams will be online, okay? If we have anything on the lab, it will just be for the lab itself. If for some reason we need to borrow some time for the lecture, we will do that. But as it stands right now, everything will be in the lecture part will be online, okay? All right. So these conversion factors here, that 1 inch is equal to 4.54 centimeters and so forth, all of these right here are given to you on the shapes table, okay? So you don't have to memorize those. Those factors are allowing you to go from English units to metric units, and we give you that. Now, within the English units and within the metric units, that's on you. Those are factors that you need to work through, like that table I just showed you, going from centimeters to meters, micrometers, etc. Okay, but these 3 units will get you from inches to centimeters, which can send you to kilograms. Kilometers. Right. Every factor can set up as the following ratio, where you got inch in the numerator or invert it and get inch in the denominator. Which factor you utilize depends on the question and what unit you're looking for. And this is true for any ratio. We had talked about density. Remember that physical property density, where we had mass over volume. Okay, that's a ratio. We can write it as grams over milliliters or milliliters over grams. That's true for any ratio, like your wages, $50 per hour, 1 hour for $50, okay? Or your speed, 100 miles per hour. Now, eventually we're going to get to the point when we apply this technique to chemical reactions using the coefficients that I showed earlier in the chemical reaction. You're going to set up, at least at the minimum, 3 factors to get us from point A to point B, okay? And I will show you before the next chapter, a really crazy conversion question that just, you first look at it, there's no connection between apples and oranges, so to speak. But I'm here to tell you, if you have conversion factors and if you set them up properly, yes, you can get from apples to oranges. And that's the example, not that example, but I have an example that's kind of way out there, but extreme. And it is extreme on purpose to demonstrate that. Just a quick review on algebra. Just remember how units can cancel, like units can cancel. Refresh your memory on units and how they cancel or how they add if needed down the road, okay? Nothing complicated. We have this here that I'm gonna save it for the chapter, but this is a kind of a picture to kind of help you with in English units, where you get from gallons to quarts to pints to cups, okay? We'll see that here in a bit. All right, so let's talk about math skills. All right, so there are in your module, there are some worksheets about this. Work through the problems. They really will help you. Like any mathematics, the more you do, the better you get, the more confident you get in doing the mathematics. Okay. Well, measurement is a number with a unit. That's the important part. It's a unit, because without units, that number doesn't mean anything. If you make the comment 8, and what does that mean? In science, we got to be very specific. Okay, and so we're talking about 8 pounds, 8 tons, so on and so forth. We have to be very specific, and that's where units are quite important. Okay, now this whole chapter and the next one deals with accuracy and precision, okay? Now, I realize that when you take two numbers on the calculator and you multiply, divide, and do whatever mathematical function to it, your calculator can spit out maybe, a dozen numbers, okay? Now, that doesn't mean just because the calculator spits out a dozen numbers that you would write that as an answer, okay? Because you may have a number in the calculator with 6 decimal places, but that would be incorrect to present that number, because here's a takeaway about all this in a nutshell, all this mathematics, is this. The answer that you present, okay, cannot be more accurate than the least accurate number you use in your mathematical function. Okay, so if I do any add, subtract, multiply, divide, okay, I'm going to learn, first of all, to learn which one is the least accurate number. And from that information, if I use those numbers in any multiplication, division, addition, or subtraction, my answer cannot be more accurate than the least accurate number that I utilized in the mathematical function. Does that make sense? Okay. Yes, I know the calculator spits out, 10,000 numbers. That doesn't mean that that makes it accurate, because what drives the accuracy is the measurement that you utilize. Everything that you use to measure anything has a degree of uncertainty, okay? That last number, you may have a ruler where you're trying to measure the length, and we're going to do this coming Friday. We're going to do measuring things. But you may have a ruler that, maybe doesn't have as many increments, is not as accurate, compared to another ruler has more increments. So I can be more accurate. I can have more decimal places with a more accurate ruler than I can with one that has least increments. The same analogy would be if I had to measure distance, and let's say I'm trying to measure the length of this wall here, I may have a laser beam that I can shoot up against the wall and get a number based on this laser beam that's there, okay? Or I can sit there and eyeball it with my eyes and guesstimate and say, it's about 30 feet. And then my laser comes up and says, actually, it's about 31.682. Well, obviously, the 38.612, whatever number it came up with, is the most accurate than my eyeball. But if I take those two numbers, the number I measured with my eyeball and the number I measured with the laser, and I multiply them together, or I divide them together, okay, or I add them or subtract them together, my answer should be no more accurate than that number that I used my eyeball to measure, because that is the least accurate number I have, okay? That's the whole gist of this whole thing. All right, the units, where I introduced those earlier, we have centimeters, millimeters, meters, and kilometers. Okay, in science, we use a metric system, so we're going to put a lot more emphasis on that. All right, you can see here, I just mentioned about rulers. The ruler in white has less increments as compared to the ruler in brown. That means that you would have less accuracy with the right ruler. If I were to, let's say, what if I were to measure this distance here of that arrow, okay? If you look at that, what would you say that arrow using a white ruler, what would you think that value would be? I put the ruler in the same spot, 0, but using a white ruler, what could you say about the measurement for that arrow from point to point? What would you think? What's your best guesstimate? Would you say, we're looking at this, this is the 4.5 mark right here, right? And so I'm looking at the tip of the arrow somewhere around there. I don't know, maybe 4.5, maybe 4.7. Okay, that's reasonable. You may see 4.8 or you may see 4.6, and that's okay. It's that last number that has a degree of uncertainty. You're going to notice that when we balance, we use the balance, electronic balance, that last number may be fluctuating a little bit because the vibration of the building and so forth, and it's causing that balance is so sensitive to fluctuate. And so you end up doing just, picking a number that pops up, the last number, I should say. And that's where the degree of uncertainty. Every tool that is made to measure anything, be it length, volume, mass, has a degree of uncertainty. There is no tool out there that is 100% accurate. There's always a degree of uncertainty. Now, if we look at the bottom ruler, now we got now we got more increments, so we can go 4.5, 6, 7 for sure, and then maybe about halfway. We could say roughly 4.75. Okay, let me change the color. It's hard to see that. Yeah, 4.75 versus 4.7. So you can see that the white measurement, we can go to the 10th decimal place, where the brown can go to the 100th decimal place. So the white one is only accurate to the 10th place, and that is the least accurate. And so if I were going to take these two numbers, 4.7 and 4.75, and for some reason I'm going to multiply these two numbers, the final answer should have no more accuracy than that 4.7. And we're going to learn how to determine that, okay? How to determine how many digits does our answer have at the end. Okay. All right. Mass, we use milligrams, kilograms, and grams. The balance on the right is very similar to the balance you're going to use in the lab. I did introduce the balance on the left. Obviously, the one on the right has a lot more accuracy, okay? A lot more accuracy. Looks like from the picture, I can go maybe 3 decimal places. The one on the left, I can probably go maybe 2 decimal places. All right. Mass versus weight, there is a difference, okay, because weight is a measure of the force of gravity, okay, and is denoted by the following relationship where you got weight is equal to your mass times gravity. Here on Earth, gravity is a constant number, I believe it's 9.8 meters per second square, okay, and we take, excuse me, making my eyes very itchy. So there is a relationship, that is the relationship of weight and mass. Mass and weight are different, okay? And so an astronaut that weighs 170 pounds would be, roughly 29 pounds on the moon, because the force of gravity is much different, much less on the moon than it is on Earth. However, the mass remains constant. Whatever mass I have here on Earth, which is a measure of all the matter that I have on my body, is the same as on the moon, okay? Now, we tend to interchange weight and mass as one unit here on Earth because, we're stuck on the Earth. And so, yeah, sometimes you'll see what is the weight, they're talking about what is, or you may read what is the mass. We're talking about the weight. We're going to interchange it now. If we were up in space, we have to be more specific, okay? All right, volume, we use the units of liters, kiloliters, milliliters. These are some of the glassware to describe how we measure it. Now, the thing to note about here, this is when you look at the glassware to measure volume. If you look at this one, this is a graduated cylinder. The 0 point starts at the bottom and we measure up, okay? So we got to be careful if we're measuring the liquid of the volume of liquid, make sure you note where the 0 point is for the glassware. Over here, in this one, it's called a burette. That's when we want to dispense an accurate amount of liquid. The 0 point is on top, and we go down this direction, okay? So, you got to be careful when you're going to read that unit for the volume and make sure you are reading the right number. You might be calling it 10, but it's really 9 or vice versa, depending on where you started for the scale. Okay. Syringes, for example, you may be familiar with the unit CC, which is just cubic centimeter. Okay. And there is a conversion factor of 1 milliliter is equal to 1 cubic centimeter or 1 cc. Okay, so we have another ratio here. If I need to convert to millimeters to centimeters or vice versa. But you don't really need that conversion factor because the numbers are 1 to 1. So if I have 1,000 centimeters, guess what? I have 1,000 milliliters, okay, because it's a 1 to 1 relationship. Now, when we read, with more on this in the lab, but when we read a volume, it creates what we call a meniscus. And because of the properties of the liquid in a cylinder, you form this concave shape. That's the meniscus. Now, what we do is we look to bring that cylinder up to eye level, and we look in that direction, and we look at the bottom of the meniscus, and that is where we take the measurement. So you see it's a little bit ambiguous, right? Because the question is, do I read on top of the meniscus or the bottom? So it's understood that we're always going to read at the bottom. Now, if for some reason there are some liquids that the meniscus goes the other direction, no worries, same scenario. We read at the top of the meniscus. You're not gonna get this very often. The majority of the time, the meniscus is going down in what we call the concave. Okay. Point 1 about reading the volume here, as I stated, check your 0 point. So this is 0 at the bottom, so we're reading up. Look at your scale. It looks like these are increments of 1. And so this here happens to be, here's 20, this is 21. And so we're going to guesstimate, and there's 22. Okay, so we're going to guesstimate between these two numbers. Okay, so we're only accurate to the 10th place. If there were more increments in between, it could be like that ruler with more increments, be more accurate to the 100th place. But at the most, we can be at the most accurate we can be is to the 10th place. So this would be, I don't know, 21.7 milliliters. Okay. The last one is always has the uncertainty. It could be 21.7. It could be 21.6. Now, what's happening is this. I read 21.7. But somebody could read 21.8, or some could read 21.6. Notice the range from here to here is 0.2 milliliters, okay? If we were more accurate, and let's say it was 20.70, well, the last number is always a degree uncertainty, then it would be 21.71 at the max, 21.69, okay? I read maybe 0.70 if this cylinder was a lot more accurate. And look at the range now, okay? 0.02 millimeters. The range of air is much less when you have more increments compared to when you have less increments, because this one here is a lot less accurate than one with more increments to read the numbers. Okay. All right, which brings us to what we call significant figures. Okay, I had mentioned earlier that we're going to do mathematics, and that when you present an answer, you have to present an answer with the number of digits that are represented by the least accurate reading. Okay. And the way we do that, how we determine that, is we use what I call significant figures or sig figs. Now, when we say significant, it doesn't mean that that number, we say it's insignificant, we don't mean that it doesn't play a role in the value of that number. It does, okay? It plays a role. It is insignificant or significant when we present the answer with the correct number of digits. That's it, okay? So we don't ignore its magnitude, if you will. We don't ignore its contribution to the full value of the number. We ignore its contribution to the final answer with the correct number of digits. Okay. All right, like we were doing earlier, we can obviously, we have this measurement here. The top ruler has the least number of digits. So at the most, we can go to a tenth of a decimal, 1/10 of a decimal place, whereas the one in the bottom, we can go at least to 100 place, 0.01. Okay, again, because the instrument is less accurate with the top one. Okay, now there's some rules about determining whether a number is significant. Now, all numbers from 1 to 9 are considered significant. Okay, so this number, 4895.2, all of them are integers, all of them are numbers, okay? Therefore, this has 5 sig figs, okay? 5 sig figs. Any of the leading zeros, okay? Any of the leading zeros. So I'm going to go through the rules, and then I'm going to simplify them for you to determine whether a number is how many sig figs. It's the zeros that confuse the students. There's no question about numbers 1 through 9. They're significant. It's the zeros that kind of play havoc a little bit, okay? Now, the basic rule is this. If it's a leading zero, basically, if it's a number less than 1, those zeros are just putting us in the decimal place position. They don't play a role in being significant with respect to the final answer, okay? So, and so that means that the 0.000, the zeros up front, are not significant. Okay, so we can't ignore them. We're not ignoring them. We're ignoring them only because they won't be used to determine how many sig figs. So we just temporarily ignore them. So there are only 4 sig figs here, and they're 4 because the 5, the 4, 5, the 4, they're integers as per rule number 1. Okay. Now, the next one. When zeros are in between 2 integers, they count as being significant. Okay. Okay. Somebody's knocking on the door. Let me pause this for a second. Nobody's here. I gotta answer it. Give me 5 minutes. All right, I'm back. Some little kid. I just noticed your chats. That's a good idea. You have a chat group. You know, better than that, don't forget we do have you do have tutoring online. I believe they offer online, pretty sure, but on campus. Also, you know, you guys can do Zoom. You know, set up a group and set up your own Zoom. One of you get Zoom or WebEx or whichever you want to use to get together. Okay. All right, let me go back to where I was. We were talking about sig figs. Okay. Now, numbers, zeros, only zeros that are in between whole numbers, they are considered significant. So the number 3050 has 3 sig figs. Obviously, the 3 and the 5 count because as per rule number 1. And the 0 between 3 and the 2 counts because it's captive. The 0 at the end, hold on. The 0 at the end right here is not considered significant with respect to figure out the number of sig figs in your answer. It is significant because it tells you you're in the 3,000 range. This is important to get. I wish that there was a different term that the book uses other than significant, because this is what happens, with students. Okay, you have that number right here. We have 3 sig figs, so this one counts, this one counts, this one counts as 3, overall has 3 sig figs, okay? And the last 0 does not count as sig figs. So what happens is students drop that 0 and you end up with this number. Now think about it for a moment, okay? What have you done to the magnitude of that number? Maybe the better way to look at it is put a dollar bill symbol in front. $3,050 versus 305. Big difference, right? Factor of 10. And so because it doesn't play a role in being significant, does not mean you drop it. It stays there because you're in the magnitude of 3,000. Okay, you're in the 3,000. So you have 3 sig figs. What this tells you is 3 sig figs. When I do something mathematically, what we're going to learn about, I know that there's 3 sig figs, and if this is the number with the least sig figs, then this number will govern how many sig figs my answer will have. Okay. Okay. So we're not talking about we don't even the term value could, it kind of gives it a different connotation also. We haven't come up with a better word. All right, let's look at the next number. These 3 zeros, okay, as per rule number 2, are considered insignificant. They are significant because they hold the decimal place, but do not play a role in determining the number of sig figs. These 2 zeros between the 2 and the 1 are considered significant because they're captive zeros, okay? So therefore, there are 4 sig figs in this particular number, 4 sig figs. Now, with those examples there, if I were to do mathematics here between these 2 numbers, and let's say for right now, let's just say we're going to multiply those 2 numbers, okay? The top number only has 3 sig figs. That means that if I were to multiply or divide, divide these numbers, then my answer should have no more than 3 sig figs. That's what we're trying to determine, okay? My answer should only have 3 sig figs because this number is the least accurate number than this number, okay? All right. Now, trailing zeros. Okay, so let's take a look at this number here. The first 2 zeros are, as per rule number 2, do not play a role because they're leading zeros. And then the last zero, we would think that they wouldn't count. However, if there is a decimal point and an integer, then they do count. Okay, so if we look at the last zero is in front of an integer, and there is a decimal point in that number. So therefore, that 0 does count, and we have 3 sig figs. Okay. Now, if you look at these here, yes, there is an integer in front of those 2 zeros, but there is no decimal point anywhere in this number. So those last 2 zeros do not count, and this number only has 3 sig figs, which kind of summarizes the rules if you think about it. Integer, automatically, no question asked, okay? And so for any other 0, and it's only for zeros, If you answer yes to the two questions, and one question is there an integer in front of that number? And is there a decimal point anywhere in that number? If you answer yes, yes, then those zeros count. For example, 100, okay? We look at the two zeros here. We can either say, these are like this number here, cap these zeros, and then where is it? Trailing zeros. Well, let's simplify. Look at the zero. Is there an integer in front of those two zeros? Yes. Is there a decimal point anywhere in that number 100? No. That means those two zeros don't count. There's only one sig fig. Okay, let's do this, 100.0, okay? Ask the question for the zeros. We know the one is significant. Is there an integer in front of those three zeros? Answer is yes. Is there a decimal point anywhere in that number? Answer is yes. That means that all those zeros count. We got 4 sig figs, okay? See how that works with a decimal point and how you ask the question?
I just have one question about that.
Sure.
So say like in a problem or whatever, it says the top option for 100. If it doesn't have the decimal, don't assume it, just take it for what it is.
Yes, yeah. Don't, unless you see that decimal point, it doesn't have a decimal point. Okay.
Okay, cool.
No assumptions. I mean, it will give you that number with or without. Okay. Now, it doesn't mean, now the question is, another question asked, is there a difference between 100 and 100.0? Is there a difference in value between 100 and 100.0? Can anybody answer that? Let me put it to you this way. Maybe if I put a dollar symbol. What's that? Is there a difference in, yeah, is there a difference in value between $100 or 100.0?
No.
No, no difference in value. But is there a difference in accuracy? Yes, because the bottom number has a decimal point. You have 4 sig figs, has 4 significant figures, whereas 100 only has 1 sig fig. Okay, so the more accurate number would be the bottom number. Okay, and if I were to kind of multiply these two numbers together or divide them or do another function that we're going to talk about, then my answer should have no more than 1 sig fig, because the 100 is the least accurate number because it only has 1 significant figure. Okay, hope you can all see that. All right. Yes. So the last one here, you got 28,500, only has 3 sig figs. You ask, if you ask about the zeros, then ask the questions, are there integers in front of the 2 last zeros? And the answer is yes, there's a 5 in front of the zeros. Then secondly, is there a decimal point anywhere in that number? And the answer is no. And so those zeros don't count as being significant, okay, with respect to determining the accuracy of your answer. They are significant with respect to magnitude. Okay, I can't overemphasize that, because even though these 2 zeros don't count, we are still in the 28,000 range, not in the 285 range. Okay. And one way to look at it, I always put a dollar symbol in there just because now you can really feel it. I got $28,000 versus 285. Okay. And obviously I don't want to drop that number because I changed the magnitude of that number. Okay. And okay, in this case, the moment you add a decimal point in that number, for those zeros, they start to count. All right, so there are numbers that are called exact, okay? Like 14 people, exactly 14 people. We're not talking about 14.3, we're exactly 14 people. And the conversion factor in 1 yard, there's exactly 3 feet. There's exactly 100 pennies, or 5 iPads, or in the 12 pack, there's 12 packs, 12 cans of beer. Those are exact numbers. When a number is exact, they play no role in determining the number of sig figs in your answer. A lot of the conversion factors we talked about earlier, the metric conversion factors, those are exact numbers. So they would not play a role in determining sig figs. Another aspect, recall the periodic table, that number, the decimal number under the symbol, okay? You would think it being a decimal number that would play a role in your sig figs if you use that number. But no, for the atomic weights of all the atoms on the periodic table, they are not used in determining the sig figs. And the reason they're not, because they are the average of whole numbers, okay? And when you have an average of whole numbers, you have an infinite number of significant digits. If I say to you, I got a whole number of 11 and 12. Well, the average between those two numbers is 11.5, right? I add them up, divide by 2, that's 11.5. That's a decimal number. And so that is not a whole number. And so therefore, the atomic weights on the periodic table are never used to determine sig figs, even though you're going to use them for calculations, okay? Treat them as an exact number. Things that are not exact, that is something that you measure, as I described earlier, that any measurement has a degree of uncertainty, especially in the last number. So 7 inches, 200 pounds, 10 ounces, those are all measurements. You used a tool to measure it, and therefore could play a role in determining the accuracy or determining how many sig figs your answer would have, okay? Sig fig rules don't apply to exact numbers. And then let's take a look. Let's take a look at these, and then we're about halfway done. We'll call it a day. All right, so let's take a look at the first one. Okay, 5.05. Okay, there's a question. That is correct. There's because the unit is 3 feet per yard. That's an exact number. It's not 3.1, and they're not measuring 3 feet. They're telling you that the 3 foot in itself is a measurement, but those 3 of those is equal to 1 yard. So therefore, it's an exact. Okay. All right, first one, 5.05. So we know the integers are count. So obviously there's at least 2 sig figs. The question mark is at 0, okay? So you ask yourself the question, you can, 1 or 2 ways to look at this. You can say, okay, that 0 is CAFT with 2 integers, so automatically it counts, and that's true. Or you forget that, you say, all right, I got a 0. Is there an integer in front of that 0? Yeah, there's a 5. Then is there a decimal point anywhere in that number? Yes, there is. So therefore, the 0 counts, the 5s count. I have 3 sig figs. Okay. All right, 1200. Same. We know the 1 and the 2 count as being significant. It's the zeros. They're trailing zeros. Normally, by that rule, trailing zeros don't count. If you forget that, then remember the 2 questions. Is there a decimal number in front of the zeros? Yes. Is there a decimal point anywhere in that number? No. With a yes and a no, that means that only the 1 and 2 count as being significant. The zeros count as far as magnitude, but with respect to significance in your answer, they do not. All right. Let's look at the next number, 0.02020. Okay, let's look at the first 2 zeros. They're leading zeros. By that rule, they don't count. But again, if you forget, let's focus on the first 2 zeros. Is there an integer in front of those first 2 zeros? Answer is no. Automatically, they don't count, okay? The second zero, the zero between let me mark this. This zero, the rule says it's between two integers, they count, but we may have forgotten that. So let's look at both zeros together. In both cases, there's an integer in front of them, so they count. Secondly, there is a decimal point in that number, so they count. That means that they're all 4 sig figs. Okay. Next one, leading zeros. But again, ask the questions for those 4 zeros. There's no integer in front of them, so they do not count. There's only one significant figure in that number. 50, same thing as a trailing zero. That zero doesn't count. There's only one sig fig, okay? No decimal point in there, so that zero don't count. Does not count. 50.00, yes. For those 3 zeros, there's an integer in front of all 3 of them, which is the 5, and there's a decimal point, and therefore they all count. Now, both of them had the same value, 50 and 50.00. They both had the same value of magnitude, okay? Where they differ is accuracy, okay? The 50 could be me eyeballing the length, 50 feet of the room. And the 50.00 could be maybe a laser beam measuring the length of that room. Okay, the 50 is the least accurate because it's an estimate. That zero, there's the true value can be anywhere from 49 to 51. Okay, which is like 2 feet range. All right, the 1, 2, 3.45, all of them are integers. Automatically, they all count. And then finally, the last one has 3 sig figs. The last zero does not count, okay? The zero between the 8 and 9, they count because they are trapped between 2 integers, okay? Any number trapped between 2 integers count. All right, so now that we determine how many sig figs they have, now we can do, when we talk about the mathematics, we separate the 2 types of mathematics we're going to do. We're going to multiply and divide, which is governed by the number of sig figs. When we add, subtract, their final answer is governed by the number of decimal places, okay? Let me repeat that. When we multiply and divide these numbers with each other, the final answer, the sig figs, is governed by that number of the least number of sig figs, okay, which is the least accurate number. When we add and subtract, what governs the accuracy of your final answer is that number with the least number of decimal places. And we'll have more examples here to explain that. All right, so let's do this. I got 241. I went over a little bit. All right, slide 17. Let us, I guess I have no choice. We got to continue next week. All right,